This is called the first derivative test. The first derivative test is a way to use the first derivative to determine where the original function is increasing and decreasing, and also where it has relative maximums and relative minimums. So first, I'm going to give you an example of how we can use the first derivative to determine where a function is increasing and decreasing. So we have the function x cubed minus 3/2 x squared. So I'm just going to give you a picture of what this one looks like. It has this basic shape. Okay, well, if you mark it, I'll mark in blue where we're increasing, and then in red where we're decreasing. If you notice, the spots where we change from increasing to decreasing, or vice versa, also happen to be the places where the derivative is equal to 0. And that turns out to be true in general, not just in this problem. Our functions change from increasing to decreasing where our derivative either is equal to 0 or does not exist. In other words, the critical numbers. So I'm going to take the derivative of my function and set it equal to 0. This won't have a place where it doesn't exist, so we'll just focus on where it equals 0. Factor out 3x, then set both pieces equal to 0, and you should find that x equals 0 and x equals 1 are the two critical numbers. Now there can be no critical numbers, there can be 1, 2, 3, there can be any number of them. But now that we found the critical numbers, what we want to do is split the graph up. So again, let's look back at the picture I drew. Basically, you have three places. You have 1 here, 2 here, and then 3 over here. 3 pieces. And place number 1 starts way over at negative infinity and then stops right here. 2 starts here and stops here. 3 starts here and then goes on to positive infinity. So we're going to create a similar scenario down here using our critical numbers. We're going to start at negative infinity and go to our first critical number, which is 0, and then go from 0 to our next critical number, which is 1, and then from 1 to infinity. Just think about a number line, basically. This going out to negative infinity and this to positive infinity. And we're breaking it up at 0 and at 1, which creates 3 intervals. Negative infinity to 0, 0 to 1, and 1 to infinity. You're pretty much always going to start at negative infinity and go to positive infinity, and then use your critical numbers as boundaries. So now that we've created these intervals, we're going to make a table. And I want to test the first derivative using this table. Okay? So here's the idea. We want to test to see on these intervals whether the first derivative is negative or positive. So I go to the first interval, negative infinity to 0, and I just pick any number in between. You can pick whatever you want. You can do negative a million, negative 5, negative 1, anything, as long as it's between those two numbers. I'm just going to pick negative 1. Now if you look, both this equation and this equation are the derivative. The second one is just factored out, but they're both the derivative. All we really care about is whether the derivative is negative or positive, so I'm not even going to worry about the numbers they equal, just the signs. So I find it easier to plug it into that second option, the one below, that's 3x times x minus 1. So for example, if I plug in negative 1, I get a negative 3, and then a negative 1 minus negative 1 is negative 2. So I get a negative times a negative, which gives me a positive. So on the interval negative infinity to 0, the derivative is positive. And that should be true anywhere on that interval. You could plug in any of those numbers and you get a positive result. Okay, now let's go to this one. Let's say we plug in 1/2 between 0 and 1. 3 times 1/2 gives you a positive. 1/2 minus 1 gives you a negative. And a positive times a negative is a negative. Okay, and then over here I'll just pick 3. You could pick 2, 4, 8, 400, doesn't matter. And if I go back here, 3 times 3 is a positive 9. 3 minus 1 is a positive 2. So I get a positive times a positive, which is a positive. So I've now used the first derivative to test where the first derivative is positive or negative. So now let's think about what that's going to mean for our original equation. Well, if the first derivative is positive, that means we also know our slope on our original is positive. And if you have a positive slope, that implies that you are increasing. So if the derivative is positive, the original is increasing. Again, the flow of logic here is that our derivative is positive. That means our slope is also positive. And if we have a positive slope, we are increasing. So next, we have a derivative that's negative from 0 to 1. That means our original has a negative slope and is decreasing from 0 to 1. And then same logic on the end. Positive derivative means positive slope, means you are increasing. So a positive derivative will always mean your original is increasing, and a negative derivative will always mean your original is decreasing. And we've just used the first derivative test to determine where things are increasing and decreasing. And just briefly, I want to explain why this is important. I know for those of you who've grown up with graphing calculators, and that would include me, this seems a little silly because why not just plug it in a calculator and look at the graph? You've got to remember, graphing calculators are pretty much just 20 or 30 years old. At least things that wouldn't fill up a room or require major computing power. So for hundreds and hundreds of years, there was no way to see a graph unless you really wanted to make a very detailed one by plotting points, and that was just very tedious. So if you wanted to know where something was increasing and decreasing and try to get an idea what the graph looked like, this was a really powerful and relatively short way to do it when you didn't have a calculator or a computer that could graph it for you. Next example. Find the intervals where f of x equals x squared minus 4 to the 2/3 is increasing or decreasing. Same process. We need to first find the critical numbers. To take the derivative of this equation, we're going to need to use the chain rule. So I do the derivative of the outside times the derivative of the inside. Okay, if I do a little simplifying here, I get 4x over 3. And then I'm going to move that to the negative 1/3 part down to the bottom. So it gives me this. Now again, critical numbers are where you equal 0 or don't exist. Well, a fraction equals 0 when the top of it equals 0. And if you look, x equals 0 will make the top 0. And if the bottom equals 0, you don't exist. So that's also one of our critical numbers where we don't exist. So looking at the bottom, what values will make the bottom not exist or equal 0? Well, that would be -2 and +2. So we have 3 critical numbers this time. So again, think about a number line going from -infinity to +infinity. We're going to have marks at -2, 0, and 2. So this time we're going to have 4 intervals when we set up our table. They're going to be from -infinity to -2, -2 to 0, 0 to 2, and 2 to infinity. So now we can take our points, pick test points, things in between these intervals, and plug them back in our derivative. Now you can plug them in any version of the derivative you want. You can plug them in up here, you can plug them in here, or in here. I tend to use the most simplified, so I'll use that very last one. Okay, if I take a -3, we'll use black for this. If I take a -3 and I plug it in up top here, that's going to give me a -12. If I plug -3 in the bottom, -3 squared is +9. 9 minus 4 is positive, so I'm going to get a positive on the bottom. Negative divided by a positive is negative. Now between -2 and 0, I'll probably pick -1. If I put -1 in the top, that gives me a -4. If I put -1 in the bottom, I get -1 squared, which is +1. But then 1 minus 4 is a -3. And I know anything I do from there on, it's going to be a negative. So I get a negative divided by a negative, which is a positive. Okay, then from 0 to 2, I pick a +1. And you could do 1/2 or 1½ if you wanted to. And I'm just going to use 1, just keep it simple. If I plug 1 in on top, it's a positive. If I plug 1 in on the bottom, 1 squared is 1. 1 minus 4 is -3, so I get a negative. Positive over negative is a negative. And finally, From 2 to infinity, I'll just pick 3. I put a 3 on top, I get a positive 12. 3 on the bottom, 3 squared is 9. 9 minus 4 is a positive number. So positive over positive gives me positive. So using the same logic we did on the previous one, if the derivative is negative, the original is decreasing. And if the derivative is positive, the original is increasing. So now we know that this function is decreasing from negative infinity to negative 2 and from 0 to 2, and increasing from negative 2 to 0 and 2 to infinity. Okay, one more example with increasing or decreasing. Find where f of x equals x squared plus 1 over x is increasing or decreasing. Now just so you know, you can use the quotient rule on this one, or you can just simplify by doing x squared over x plus 1 over x. That is up to you. I find that doing the quotient rule is going to make the test part of this easier. It may not be the easiest way to do the derivative, but to me it makes the rest of the problem simpler. So that's what I'm going to do, is just use the quotient rule. So I have f and I have g, and remember the quotient rule is f prime, which would be 2x, times g, minus f times g prime, which would just be 1, all over g squared. So simplifying, I get 2x squared minus x squared minus 1, because this negative applies to both of those, all divided by x squared. So that's x squared minus 1 over x squared. Again, when you're dealing with a fraction, this is the derivative. I should have written that somewhere here. This is the derivative. When we have a fraction, if the top is 0, the whole thing is 0. If the bottom is 0, you don't exist. So when you're looking for critical numbers, you just see what will make the top 0. Well, that would be negative 1 and positive 1. What will make the bottom 0? That would be 0. So I get negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. And you can draw that number line if it helps you, but I think once you do a couple of these, you'll be able to see it pretty clearly. So now we need to pick test points to plug into the derivative. Alright, so I'm going to pick negative 2 to start with. If you notice, anything I plug in the bottom here is going to be positive, so I don't really even have to worry about it. I just have to see what it's going to do to the top. So if I plug negative 2 in the top, negative 2 squared is positive 4. 4 minus 1 is positive. Sorry. Here we go. Okay, now I'm going to pick, say, negative 1/2. Well, if I pick negative 1/2 and put it in the top, negative 1/2 squared is 1/4. 1/4 minus 1 is negative. So now between 0 and 1 I can pick 1/2, plug it in top. 1/2 squared is 1/4. 1/4 minus 1 is negative again. And then 1 to infinity, I'll just pick 4. 4 squared is 16. 16 minus 1 is clearly positive. You may have wondered after my first two examples if it just always alternates positive, negative, or negative, positive. The answer to that is usually it does. Probably over 90% of the time it does just alternate. But one reason I did this example is because it doesn't always. You really do need to finish the problem out and not just assume it's going to alternate, because occasionally it does not do that. So if we use our knowledge, we know that if the derivative is positive, that means the original is increasing. And if the derivative is negative, the original is decreasing. So that's how you determine whether a function is increasing or decreasing on certain intervals. Now if you notice and go back to the beginning, I've only given you half the picture here. I've done this part for you. I've showed you where to find a function is increasing or decreasing, but we haven't touched the second part. You're thinking, oh gosh, this video is already too long. What's going on? Well, the relative max and min are actually really easy. If you've already done the increasing and decreasing part like we have, the max and min is a piece of cake. So I'm just going to go back through these same three examples and show you how to find the relative max and relative min using the first derivative test. So let's look at this one. This is our first example again. All you have to do is draw a very, very simple sketch of your picture. For example, we know that from negative infinity to 0, we are increasing. And then from 0 to 1, we're decreasing. And then from 1 to infinity, we're increasing. So right here at this point is 0. And just look at the picture. What would we have right here at 0? Well, we'd have a maximum. It's a peak. So we have a maximum at x equals 0. And then right here at 1, that's right here, we have a minimum. So it's that simple. Now notice, some people get thrown off because they're like, wait, how can the maximum be 0 and the minimum be 1? 1 is bigger than 0. We're talking about the x values. So that has nothing to do with how high or low you are. That's just where you are left or right. So that just means the maximum comes before the minimum. That's all that means. And remember, these are relative max and mins. There could be higher points elsewhere on the graph, but these represent a peak or a trough, or a valley if you want to call it that. So second example, let's look at our chart again. We go decreasing, increasing, decreasing, increasing. So right here, we're going to have a minimum at -2. Right here, we have a maximum at 0. And right here, we have another minimum at +2. So a minimum at -2 and +2, and a maximum at 0. Now just so you know, you can have any number of these. You may sometimes have just one min and no max, or one max and no min. You may have one of each. You may have two of one and one of the other. So there can be a lot of variety as far as that's concerned. Now let's look at the third one. This one goes increasing, decreasing, decreasing, increasing. So notice right here at 0, that's neither a max nor a min. It's not going to give you either one. But we do have a maximum here at -1 and a minimum here at +1. So that's how you use the first derivative to find the relative max, the relative min, and what intervals over which it is increasing and decreasing.